In our last video, we built our first machine learning model, Simple Linear Regression. One input, one output, one straight line. We took temperature and predicted ice cream sales. Clean, simple, and a great way to understand the fundamentals. But real-world problems are rarely that simple. In the real world, an outcome usually depends on many things at once, not just one. So instead of one input leading to one output, we now have several inputs, all feeding into a single prediction. Think about predicting the price of a house. The price doesn't just depend on one thing. It depends on the size of the house, the number of bedrooms, the number of bathrooms, the age of the property, the crime rating of the neighborhood, the size of the lot, and often, many more factors all at once. That's exactly what we're going to work with today. Take a look at this dataset, housing prices. Instead of one input column, we now have 6. Square feet, bedrooms, bathrooms, age, crime rating, and lot size. And just like before, our output, the value we want to predict, is the price. Now, we have 6 features feeding into one output. We've gone from 1 dimension to 6. So here's our problem. A house comes up for sale. We know its size, bedrooms, bathrooms, age, neighborhood crime rating, and lot size. The one thing we don't know, its price. Can our model predict it? We can't draw this on a simple graph anymore. But the underlying idea, finding the relationship between inputs and outputs, stays exactly the same. This is multiple linear regression. Same core concept as before, just scaled up to handle real-world complexity. Before we train our model, let's take a quick look at how each feature relates to price. Here are individual scatter plots for each feature plotted against price. Across these features, the pattern is still linear. A straight line fits reasonably well in each case, but the direction isn't always the same. For most features, price tends to increase as the value goes up. But for something like crime rating, it's the opposite. As crime rating rises, price tends to decrease. And that's perfectly fine. A linear relationship doesn't mean the line has to slope upward. It just means a straight line is a good fit. Some features push the price up, others pull it down. The model will learn which is which, and by how much for each one. So before we jump into the code, let's look at the equation behind multiple linear regression. This is the general form. Y hat equals W naught plus W1 times X1 all the way to Wn times Xn. Notice the shape of this. It's the exact same idea as simple linear regression. Y equals Wx plus B, just extended. Instead of one weight and one input, we now have a weight for every input. W naught is our bias, the starting point, and each W after that is a weight, one for every feature. Now let's apply this to our housing data. Here's the same equation, but instead of generic x's, we plug in our actual features. 6 features, 6 weights, plus 1 bias. That's 7 numbers in total, and that's exactly what our model needs to learn. Each weight tells us how much that feature pushes the price up or down. Remember, we saw earlier that most features push price up, but crime rating pulls it down. That'll show up here as a negative weight. So how does this equation actually get used? It happens in 2 stages. First, training. We feed the model houses we already know about, their features and their true prices. The model's job is to find the values for 7 weights that best fit this data. Features and prices go in, weights come out. Second, prediction. Once those weights are fixed, we can plug in the features of any new house, one the model has never seen, and the equation gives us an estimated price. Weights are known, new features go in, and out comes our prediction. This is the same 2-step process we used in simple linear regression. Train once to find the weights, then predict again and again using those same weights. Now let's see this in Python. Before we dive into the code, one quick thing. Everything you're about to see, all the code and the dataset we'll be using, is up on GitHub. The link is in the description below so you can follow along step by step, run it yourself, or just keep it handy as a reference. Alright, let's start in Visual Studio Code. I've already set things up, a dedicated folder for this part, our data CSV dropped inside, and a fresh Jupyter notebook ready to go. If you're following along, grab the dataset from the link in the description and do the same. First up, data preparation. We begin the same way we did in Part 3, by importing Pandas. Pandas is the library that lets us load and work with data in a clean, table-like format. We give it the alias PD, which is just a shorthand convention so we don't have to type the full name every time. Next, we load our data. Using pd.read_csv, we read the housing file and store it in a data frame. Think of a data frame as a spreadsheet living inside Python, with rows and columns we can work with programmatically. Then a quick check. We print the total number of entries and call head to preview the first 5 rows, just to confirm everything loaded the way we expect. And there it is, 100 entries in total. Across the columns we've got our 6 features: square feet, bedrooms, bathrooms, age, crime rating, and lot size. And finally price, the value we're trying to predict. Notice this dataset already comes with exactly the 6 features we mapped out in our equation. No extra columns to strip away, nothing to rename. Clean, focused, and ready to go. So let's keep moving. Now, before we go any further, let's talk about data cleaning. In Part 3, our ice cream data was already neat and tidy, so we skipped this step entirely. But real-world data is rarely that kind. It comes with gaps, duplicates, typos, and values that simply don't make sense. And if we feed that mess straight into our model, it'll learn the wrong patterns. So before we train anything, we need to clean it up. Take a look at the spreadsheet for a moment. I've highlighted a couple of problem rows. Over here, there's a missing value, a bathroom count showing up as NA with nothing recorded at all. And down here, a price listed as a 10-digit number, clearly not a real house price. That's clearly a data entry error. These are exactly the kinds of issues we need to catch and deal with before training our model. Left in, they'd quietly throw off everything the model learns. So let's go through and fix them, one step at a time. First, we remove any duplicate rows. Sometimes the same record gets entered twice, and duplicates can bias the model toward whatever's repeated. A single call to drop_duplicates takes care of that. Next, we deal with missing values, like that empty bathroom field we just saw. Using drop_enna, we drop any row that's missing data. For now, we're keeping it simple and just removing those rows. There are smarter ways to handle missing data, and we'll explore those in a later video. Then come a few common sense sanity checks. Square feet can't be 0 or negative. A house has to have some floor area, so we keep only the rows where it's greater than 0. The same logic applies to age. A building can't have a negative age, so we keep only the rows where age is 0 or more. And finally, those extreme outliers, like the 10-digit price we spotted earlier. We filter those out by dropping any row where the price crosses a sensible upper limit. That clears out the clearly broken values without touching the genuine ones. With all that done, we print the number of entries we have left to see how much was removed. We started with 100 rows. After cleaning, we're left with 94. So 6 rows were removed in total, a mix of duplicates, missing values, and that wild outlier. And just like that, our data is clean, consistent, and ready for the next step, splitting it up for training. With our data cleaned, the next step is to prepare it for training. We split our data into 2 parts. One part is the price, the value we want the model to predict. The other part is the 6 features, the information the model uses to make that prediction. The answer side we call Y. It's just the price column on its own. The feature side we call X. Rather than list every column by hand, we take the full table and drop price. Whatever's left behind becomes our features. Now, before we move on, it's always worth pausing to check that everything landed exactly where we intended. So let's add a couple of quick print statements, one to show what ended up as our target, and another to list out the features. And there we have it. On the target side, we've got price, exactly what we wanted to predict. And on the feature side, all 6 of our inputs are present. Now that our features and target are separated, the next step is to split the data again, this time into a training set and a testing set. This split is about fairness. We don't want to test the model on the same data it learned from, so we set some aside to test it later on examples it's never seen. To do this, we bring in a familiar tool, train_test_split from scikit-learn, the same function we used back in part 3. We pass in our features and our target, and tell it to hold back 20% of the data for testing, leaving the other 80% for training. We also set a random underscore state, which locks the shuffle in place so we get the exact same split every time we run it. Running this gives us 4 sets: training features and targets for the model to learn from, and test features and targets kept aside for later. And just like before, let's add a quick print to make sure the split came out the way we expected. There we go. 75 rows set aside for training, and 19 held back for testing. A clean 80-20 split, working exactly as planned. Our data is now cleaned, separated, and split. Now let's move on to the part we've been building toward, training the model. This is where everything comes together. All our preparation, cleaning the data, separating features from target, splitting into training and testing, was leading to this single step. We start by importing linear regression from scikit-learn. Then we create the model itself. At this point, it's completely empty. No weights, no bias, nothing learned yet. Think of it as a blank template. It knows the form of the equation it's going to use, a bias plus a weight for each feature, but every one of those numbers is still undecided. It's an empty container, waiting to be filled in once we show it the data. Then comes the key line, model.fit. This is where the empty model finally gets filled in. We hand it 2 things, our training features and the matching training prices. In other words, the questions and the correct answers. The model studies how they relate and adjusts its weights until the equation fits the data as closely as it can. And that's the remarkable part. All of that learning happens in this one line. Behind the scenes, the model works out those 7 numbers we talked about earlier, the bias, plus 1 weight for each of our 6 features. We don't do any of that math ourselves. Scikit-learn handles the entire process under the hood. Now that it's trained, let's open it up and see exactly what it learned. First, we print the intercept. That's our bias, the starting point of the equation before any feature comes into play. Then we loop through each feature alongside its learned weight and print them out one by one. And here's what the model came up with. The intercept sits at around 20,000, our baseline starting point. Then the weights. Square feet adds about $140 for every extra square foot. Each bedroom, around 15,000. Each bathroom, close to 10,000. And lot size, the biggest of them all, roughly $57,000 per acre. Then look at age. It comes in negative, around -600. And that makes perfect sense. As a house gets older, its value tends to dip, so an older property is worth a little less. The model picked up on that entirely on its own. And here's the one I really want you to notice, crime rating. It's -2, at around -1500. Think back to when we first explored the data. We predicted this. We said higher crime should pull a home's price down, and now the model has confirmed it, learning that exact relationship straight from the numbers. Every weight here lines up with real-world intuition. So our model is trained, and its weights make sense. Next, let's put it to the test and see how well it actually performs. Our model is trained, but a trained model is only as good as its predictions. So now comes the real test. Up to this point, the model has only seen the training data. The test set has stayed completely hidden. So when we ask it to predict on those houses now, it's facing examples it has never encountered before. That's what makes this an honest measure of how well it really performs. We start by importing 2 metrics from scikit-learn, r² and root mean squared error. First, we ask the model to predict prices for our test houses by calling model.predict on the test features. These are the prices it thinks each house should sell for. Now let's measure how close those predictions are. The first metric is r². It tells us what fraction of the variation in price the model manages to explain. A score of 1 would be a perfect fit, while a score of 0 would mean it's doing no better than guessing the average price every time. The closer to 1, the better. The second metric is RMSE, root mean squared error. This one's especially nice because it's expressed in actual dollars, the same units as price. In plain terms, it tells us how far off our predictions tend to be on average, and here, lower is better. So let's print them both. And the results are genuinely impressive. An R-squared of around 0.99, meaning our model explains close to 99% of the variation in house prices, and an RMSE of about $20,000, which, against an average home price of over $400,000, is an error of just a few percent. In other words, the model isn't just capturing the general trend, it's landing remarkably close on real, unseen houses. But a single score only tells us so much. Let's look closer and see the predictions house by house. So we build a small comparison table. For each test house, we line up the actual price against the price our model predicted. Then we add two more columns, the raw error, the plain difference between the two, and the percentage error, which shows that gap relative to the real price. And this is where it really comes to life. Look how close these are. One house off by just 3%, another by barely 1%. Most predictions sitting comfortably within single digits of the true price. House after house, the model lands right where it should. This is exactly what a well-fitted model looks like. Strong overall and dependable case by case. With our model trained and tested, there's just one thing left to do. Return to the very question we started with and put our model to work on it. Cast your mind right back to the start. We began with a single question. A house comes up for sale. We know its size, its bedrooms, its bathrooms, its age, the crime rating of its neighborhood, and its lot size. The one thing we don't know is its price. Can our model predict it? Well, now it can. Let's find out. We take that exact house, 3,000 square feet, 4 bedrooms, 3 bathrooms, 15 years old, a crime rating of 10, and a lot size of 0.8 acres. And here's a small but important detail worth pausing on. We don't just hand the model a bare list of numbers. If we did, it would have no idea which number means what. So instead, we wrap them in a small table, a data frame, using the very same column names in the very same order that the model was trained on. This matters more than it might seem. It's what lets the model line up each value with the right feature. 3,000 to square feet, 4 to bedrooms, and so on, right down the line. Everything matches up exactly the way it did during training. With our house ready, we now call model.predict and pass it in. The model takes those 6 features, runs them through the equation it learned, and hands back a single number, its best estimate of the price. Then we simply print that result to the screen, formatted nicely as a dollar figure so it's easy to read. And there it is. Our model's answer, a predicted price of around $564,000. For a house it has never seen before, built entirely from the patterns it learned in the data. 6 features in, 1 prediction out. That's the whole promise of what we built, coming to life in a single number. And that brings us full circle. We started with a question we couldn't answer, and we finish with a real, data-driven prediction. That's multiple linear regression from start to finish.